Alrighty then. So we have some new stuff to talk about today. But before we jump into new stuff, let me find where it is. Yeah, there we go. Should have a new lecture and then 2 new examples. Depending on how long it takes to go through this stuff, I actually recorded example 5B last semester because we ran out of time to do it in class. So I may just utilize those recordings and then go through more slowly through the others. 5A is really the only part that's new. 5B is kind of a walkthrough review of all the stuff that we've talked about up to this point. So I had wanted to do a little bit of that just to help with the transition between things. But I also have your homework pulled up here in case anyone wants to ask questions. Alex, do you want to ask them now?
So only if anyone else has struggled with the first part of question 1 in SAS, setting up the coding scheme. And I think Jen has already done the homework, so he's probably good. But if Emmy or Fayaz don't have similar questions, I'm more than happy to ask it during office hours and not take up our class time.
No, you have my vote. I think you can go for it. I would want to hear the question.
Yes, also I agree.
Okay, go for it, Alex.
So, oh goodness. So really, I think it's just getting that getting the dummy coding set up with the 4 category training group. I mean, I get the idea, you know, that you'd set it up with 4 lines probably, and then tell it what to do. But I mean, we have more than 3, so it's not just low, mid, and high. So that's what's tripping me up, and it's frustrating, and I'm a little embarrassed, but you know what? I need to learn how to do it. So here I am.
Well, thank you for being brave and admitting that you need help. I think that's a really good thing because otherwise you're never going to get where you need to go. So I'll just say thank you for putting yourself out there. You are not the first person to ask me this question. So here is a spreadsheet that I put together last year, and I was waiting to see if this group was going to need it. I have an example here that I think may help, at least to start with the logic of the coding, and then we can talk about how one would actually execute it. So let me hide this silly thing here. All right, can you see this? So here's an example of what we were trying to do. You can ignore the means and the parameters here for just a second because that was based on something else. So let me make it a little bit bigger. So if I have 4 groups, I'm calling them group A, B, and C, and D, just generically. So this column is implied by the model. A fixed intercept, functionally speaking, is multiplied by a column that is just 1s for each case because each person gets the same beta 0 added to their score. So I have this here as sort of a representation, but that's not something that you need to code. In terms of the coding, what we need is to create a pattern that's going to look like this because the instructions said to make the first group the reference. And there are 4 groups in total, right? So if there's 4 groups in total, then how many predictors do I need to make to distinguish a reference group from each of the others? If I have 4 groups, how many new predictors do I need? How many new slopes?
Is that C minus 1 is 3?
Yes, it is, exactly. Because I have the intercept. So if I have an intercept and 3 slopes, that's 4 terms that will perfectly recreate my 4 possible means. That's what we're going for, is to give each group its own mean outcome, and then we'll be able to see which means are different across the group combinations. So I have taken group A as the first group here, and I have given them 0 values across my 3 new predictors. That's how I know that group A is going to become my reference. because by definition, the intercept is the expected outcome when all your predictors are 0. So by setting it up this way, I'm making it so that group A will take the intercept. Then for each of the other predictors, they take a value of 1 if it's the other group that I want to be comparing to the reference. So the reason I called this A versus B is because that's what it's going to end up representing, because the only group that has a 1 is the B group. So it's going to distinguish the B group from the A group. Likewise, this one will distinguish the C group from the A group, and this one will distinguish D from A. So relative to what we had in class with low, medium, high as our 3 groups, there's 1 new variable being created, and there's 1 new condition to fill in the new variables with. So with me so far?
Yes.
So then writing out the code, do I have that in here anywhere? Let me see. I have a whole big thing. I have logic in here, but I don't have, no, I don't have the code in here. So I can help you with the code part in office hours, but the idea then is just there's where it says if, group equals this, then do, there's 3 sets of make this, make this, make this. And there's 4 lines in total because it's if it's this group, if it's that group, if it's that group, if it's that group. So it's like you take the code that we have in the example and expand it sort of 1 column and 1 row to fill out the table.
Gotcha. And I think I added another row, but not another column, and yeah, but it's making more sense now, and I do think it might click a little more quickly than I thought it would initially. So, yay, you're the best, and thank you everyone else for letting me ask that.
I can also go over estimate statements and how we get means and mean differences, if that would be useful. Yes.
Yeah.
Yes, nod.
Yeah, I'd say yes.
Okay. Yeah, this is one of those concepts that I didn't learn until way too long. Like, I was really mad once someone showed me this. I was like, why didn't I learn this from the beginning? This would have made my life so much easier. So broadly speaking is that there's only so many pieces of information that a model is going to give you directly. There's going to be lots of other things that you want to know about your data that are implied or predicted by the model, but are not given directly. And so I want to teach you the process of learning how to ask for terms as linear combinations. Scenario. Let's change the word. In this scenario, what we have are group means and group mean differences of interest. But this same logic will also apply anytime that you have quantitative predictors and you want to create, say, predicted values for certain levels of your quantitative predictor, as well as in the next unit where we have what's known as simple slopes out of interaction terms, or conditional main effects as a function of other predictors. So this is a very general useful technique. This is one specific instantiation of it. So what I did here is just make up some numbers, all right? Let's say that these are the results of my analysis. These are the means per group for the outcome that I'm interested in. And based on this coding scheme, I can anticipate what my fixed effects are going to be. So here's my model. Let me squeeze this down just a little bit. Here's my model. Beta 0 is going to be the intercept. I don't have to ask for that. That's already implied. So that's why I have it in parentheses here. Then I have beta 1 plus A times B, or beta 1 times A versus B, beta 2 times A versus C, and beta 3 times A versus D. So A versus B, C, and D are the new variables that I've created. The B's here are going to be the betas that they take on in the equation. If I know what these means are, I know what the betas are. So by definition, the intercept is the expected outcome when your predictors are 0. So I know, because this group has a mean of 10, the A group that's my reference, that my intercept's going to be 10. Beta 1. Beta 1 takes on the difference of how the B group differs from the A group. Well, if the B group has a mean of 12, that must mean that the slope is going to take on a value of 2, because B is 2 higher than A. Likewise, if I have the difference between A and C as my parameter here, I know the slope has to be 5, because that's the difference between these two means. And finally, I know that beta 3, the difference between A and D, is going to have to be 9, because that's the difference of those two means. So everything, you only need to know 4 of these terms and you can get all the others, is where I'm going with this. If I have 4 means, I can get to the 4 fixed effects from the model. If I have these fixed effects, I can work backwards and get to these means. So all we need are 4 pieces of information and we can get all 6 terms that we'd be interested in, means and mean differences. Okay, with me so far? Now, in reality, we don't have these numbers, right? That's the whole point of doing the analysis, is to find out what they are. Well, we could actually ask it for the means per group, but we wouldn't have significance tests as to whether those means are different from each other. So that's really the point of the analysis. So if I go over here, first step would be to ask the model to tell me what the model implied mean is for each group. So some of these statements are necessary and some of them are unnecessary. The one that is unnecessary is the first one right here. The mean for the A group is already given by the intercept. Otherwise, the mean for each subsequent group is given by my model. So what I need to ask SAS to do is say, okay, I need 1 of whatever the intercept's going to be. I need 1 beta 0. I need 1 of beta 1 because I'm talking about the B group. I don't need any beta 2s and I don't need any beta 3s. So this was my drive-through analogy, right? We don't want to supersize it. We don't want to try the new Jamocha shake today. We just need a beta 0 and a beta 1. Thank you. So when SAS reads this, SAS is going to go, oh, I know what to do with this. And internally, it creates this representation. You want what the intercept is going to be? Okay, well, I know from doing the math on this that it's going to be 10. So I plug a 10 in here where the word intercept was. You asked me to multiply the intercept by 1s, so that's that. I know that the slope, beta 1, for the variable A versus B is going to be 2. So I multiply that by 1, and I multiply these other slopes I've already found by 0, and then I compute the mean. And it does the same thing then based on the mean for C and the mean for D. So the words refer to the fixed effects in the model and what they are eventually going to be. The values that you enter next to the words are the multiplier that you change based on the value of the predictor. So the 0s and 1s that I have in here correspond directly to the 0s and 1s that are in this table. Okay, questions so far? Great. So SAS does this math internally and spits out the answer along with the standard error for that mean. Now, the good news is that if you've gotten this far, if you've gotten the model right and you've gotten these 4 statements, you are home free. Because if you know how each group gets a mean, you know how the group means must differ. Because you can literally subtract one of these statements from the other to get the difference. So for instance, some of the differences here are already given to me. A versus B, A versus D, and A versus B, C, and D are already given as model parameters. I don't have to ask for those. It's the differences among the non-reference groups. They're in the model, but not directly. You got to ask for them as linear combinations. So we're focusing then on like these 3 lines right here. So if you wanted to answer the question, how does group C differ from group B? Well, here's what the model says group C is going to be. This box right here. If you put the reference for the comparison of B versus C second to make the reference, we're literally going to subtract these 2 lines. So the group C mean minus the group B mean. And I'm frozen. Are we still here?
You weren't frozen, Dr. Hoffman.
I wasn't? Okay, Fayaz was frozen and it was throwing me off. He was like, I think he's still frozen maybe. Okay, but we're all good? We're here? We're good? All right. So here's what I'm going to do. Blow this up so we can see it better. So think of this as a set of numbers that we're going to subtract sequentially. Okay, first question, what's 1 minus 1? Okay, so I put a 0 here for the intercept. What's 0 minus 1? Very good. I put a minus 1 here. What's 1 minus 0? See, I told you at the beginning of the semester that this is not a math class. This is a logic class. And finally, what is 0 minus 0? So that's where the statement comes from. It's literally the difference in how the model says each group gets a mean. So then this is the part that you would write to get how group C differs from group B. And the direction of the minus 1s and 1s is important for getting the direction of the difference. The group that is the reference of the comparison, B versus C, B is the reference, gets the minus 1, and the other group that it is being compared to gets the 1. So the end result of this statement is going to tell me how C differs from B as the reference. And so when SAS reads this, it's going to go, oh, she doesn't want an intercept. She wants the slope, but times minus 1 added to the other one works out to be 3. Same logic if I were to do D versus B here. So group B is the reference relative to D. It's D minus B. And so then it's the variable that goes with B as the minus 1, and the variable that goes with D is the 1. And then C versus D, the variable that goes with C is the minus 1, the variable that goes with D is the 1. And so there's the missing 3 that are all linear combinations. And with these coefficients, you could group them together in other ways. Like you could ask whether the average of B, C, and D is different than A. You could do things like that if you wanted to know. It's totally up to you how you play this, but this is how you would get all of the answers. So Fayaz was right. Like once you get the model right, meaning you've got all the coding right, you are home free.
Yeah, it seems like this is just a bigger version of the I think it's the chi-square, where if you have like the 4 numbers, you figure everything else out within it. So that conceptually that makes sense to me.
Yeah, it's a very similar thing. It's like I'm so old that when I took the GRE, they had an analytics section. You may have heard of that before, but it was filled with logic problems like if Bob is 3 years older than Sue and Sue is half the age of Jeremy, and you get one of the ages, then like how old is Bob? Like you can figure them all out because they're all relative to each other. It's the same exact system here. And then if you wanted to see this data code, it's over here. I didn't want to leave this data folks out. So would it be helpful for me to post this, by the way? Yes, okay, I can do that. I wanted to give everybody a shot to try this on their own before caving and posting what is very close to the answers, but you still have to do the change and manipulation. By the way, in these sorts of situations, find and replace is your friend. There's a hint that I will give you. Control H for changing out variable names and things like that. So the second part of it, enthusiasm, requires no new variables. All you have to do is enter in the linear and the squared terms into the model, and I don't believe there's any linear combinations requested in that. And then section 3 is the piecewise coding. Would it be helpful to go over that while I'm at it? Maybe pieces. So I changed it relative to last semester because I made it more straightforward this semester than what I had, but I had updated my little spreadsheet here.
Can I ask a question, Lisa?
Please.
So this question is about the interpretation of this one. And so this was one of the bigger hurdles that I encountered once I was done with the calculations, was that one of the coefficients was negative, and I wasn't sure how I could interpret that in terms of the, the mini golf scores, like, right? So if it's negative in relation to the intercept, this means that doing this would lower my score, right? Okay, so it's like, okay.
Yeah, so in theory, if you are in the mini golf training program, then being in that program should help you. And being helped translates into a lower score. Yep. So I know that's sort of confusing potentially, but there are a lot of outcomes that people study and research where smaller is better, right? Like delinquency and crime and sickness, poverty.
I'm doing one on behavioral problems where if you get a lower score, then you have less behavioral problems.
Exactly. So yes, a negative coefficient translates into a benefit in this context. Yep. Good question. Other questions on this part? All right, then the slopes. So I'm doing this in the other class right now too. The best thing that you can do to help yourself understand how to code piecewise slopes is to make a table like this. Figure out what the values should be and then write the code based on the table. So in this context, I have 7 possible levels of experience. It's an ordinal variable that I'm pretending is interval. Shh, don't tell anybody. And I have my intercept column here as a representation, and the instructions said to make experience equals 4 the reference. So that tells me that I need to create 0 values for any predictors related to experience at that point. So the instruction said that I want one slope for experience between 1 and 4 and another slope for experience between 4 and 7. So the break point of the dividing into sections is the same thing as the intercept in this case. That makes it a little bit simpler to think about. Okay, with me so far? So then relative to, if I call 4 0, what is 3 relative to 4? -1. So that's why these numbers here go negative, is because 4 is the reference point. So I'll have one variable that tracks the effect of increasing enthusiasm for people with relatively low enthusiasm. Like if you're not that enthusiastic to begin with, does being a little more than not help? But then after 4, this variable is no longer relevant. So it shuts off at 0. Then on the other one, it picks up where the other one left off. And so relative to 0 being a value of 4 being the new 0, then 5 is 1 more, 6 is 2 more, and so forth. And so then this variable picks up and measures the effect of more enthusiasm amongst relatively enthusiastic people. So the idea then is more enthusiasm helpful across the board, or is it less helpful amongst certain kinds of people? That's kind of the idea that I was trying to go for. And so once you have this coding scheme, then you can write, once you have the numbers here for the coding scheme, then you can write the syntax to do with that. And then I have syntax in here that does that. So basically thinking about this table in 4 sections, that section, that section, then this section, and this section. And so then I have if statements to help that carving process, so to speak. All right. Any questions on that? No. Do you feel better, Alex?
I do. Sure wish it made that much sense the first time, but as long as I get it in the end, I think that's what we're after. So thank you for taking the time.
It's my pleasure. My husband, since we're talking about the importance of not ignoring our people in our lives, he always has a saying that like, oh, it's so simple. It only took me like 4 days to figure this out. Because once you have figured it out, it's straightforward. But getting to that point is non-trivial. The good news is that once you've done this once, if you see something like this again, you'll be like, oh, this is kind of like this other thing I did. And then you have a point of reference that makes it easier. But it's not easy the first time. Nothing is. Nothing worth doing. How's that? Right? We all like a challenge. There's a reason you elected to keep going to school. A challenge of personal and professional development. So I'm here to challenge you. All right. So any other homework related stuff before we shift gears then? All right. Then bye-bye Excel. Hello, Lecture 5. So we are turning the corner to an exciting new section of models looking at multiple predictor variables simultaneously in a general linear model. That's where we're headed here. Alrighty. So, reviewing concepts from last time first. The role of each predictor variable in a model predicting a quantitative outcome, so staying within general linear models here, each predictor can be, its effect can be summarized by one or more fixed slopes. So its total relationship with an outcome could take just one slope or it could take more than one slope. So if I have a quantitative predictor and I hypothesize a linear relationship with the quantitative outcome, I can do that in one slope. If I have, and by the way, what is that called? Another vocabulary quiz. If I have one quantitative predictor of one quantitative outcome and I put in one linear slope, what would someone else call that?
ANOVA?
Not this one. This is quantitative predictor.
Linear model?
They would call it a simple linear regression. Yeah, not because it's easy, but because it's relatively easier. One predictor at a time. If I have a binary predictor, then by the same logic we were just talking about, C minus 1, right? I have an intercept. All I need is one slope. That gets me the two possible means. That is otherwise known as an independent groups or two-sample t-test. Same idea. If I have a quantitative predictor that I want a non-linear slope for, so if I want linear and quadratic effects or if I want piecewise effects, then it takes more than one slope to fully describe its relationship. Likewise, if I have more than two groups in a categorical variable, then what's that called, Fayaz? Say it again.
ANCOVA.
If you have a covariate, also it is.
Okay, so it's ANOVA.
Yeah, ANOVA if it's just a categorical predictor, one way ANOVA for one variable. If you add in a quantitative predictor also, but don't put its interaction term in the model, that's ANCOVA. So yeah, they have all these special labels for particular permutations of this that you will see in other people's writing and coursework potentially. I try to link it all together because it is all the same model. And so then just to recall, this is how many pairwise differences you might have. So for each of these slopes, we would get, as part of our output, an unstandardized estimate. So the term unstandardized means in units, right? Per year, per second, per dollar, per something. So you have to know what the scale is to know how to interpret the slope. You would also get a standard error. Quick review, what is the standard error for a slope? What does that tell us?
Is this where it relates something, your 95% confidence interval? Or is that
A standard error is used in making a 95% confidence interval, so I'll give you that. But you're going to answer this question like 6 times on your next homework, so I want you to get it right all 6 times. What's the standard error for a slope? Tell us.
Is it the variance between the actual and the estimated slope?
Actual versus estimated. I'm not sure those are the right words
Es
unless I'm
estimated
misunderstanding.
is one of them. Estimated
Estimated.
is one of, yeah, but and the other one is
Oh,
population.
actual is population. Gotcha. Yes, then I will take that. Yes. It is how far off on average any sample slope is predicted to be from the population slope. So you were calling estimated versus actual. I'll take it. I'll take it. You got the right idea. It is an index of inconsistency. So if I have a small sample, what happens to my standard errors? Yeah, they go up. They're more inconsistent. And if I take that estimate for my slope and divide by the standard error, then I get my friend t. T is a test statistic that tells me how many standard errors away from the null hypothesis my slope is. And a t of roughly 2-ish is where significant land starts, where you would end up in less than 5% of the time you would expect a slope that extreme if the null hypothesis was true. And so then we get an exact p-value that corresponds with that t. And then last but not least, because these slopes are unstandardized, we want to also provide some index of effect size. So taking the units off and putting the slope into terms that are more absolute. So we can do that in general linear models by asking for standardized slopes, which is the same thing as z-scoring all of the predictors and outcomes in the model, and then re-estimating the model. And I'll show you that actually in one of the examples. You can literally do that and you get to the same place. You can also take that t-test statistic and convert it into an r or a d. And r will be very close to the standardized slope, but not exact in some cases. And d is a standardized mean difference that makes more sense for categorical predictors. Okay, good so far? Good. All right. So then if I have a simple linear regression, one slope in the model, in this case, beta 0 is only conditional on x1. Conditional meaning it is the expected outcome when x1 is 0. Likewise, the slope of x1 is just given by beta 1. I don't have to think any more about it. It's the change in y for a 1-unit change in x1. The standardized slope would be the same thing as the Pearson correlation, and e is always our residual, how far off my outcome is from the one that's predicted by the model. Well, if I had another predictor that I'm interested in and I put that into the model all by itself, the exact same ideas would follow, except that it would be talking about x2 as opposed to x1. So where we're headed in this unit is putting them together. So once we have more than one slope in the model, then just looking at the t-test statistic for each of those slopes is no longer sufficient. We want to have our friend f. F then tests overall the joint contribution of the slopes in the model in a per slope metric, and it gives you a significance test for whether or not the y hat that is created by those multiple slopes, the predicted outcome, is correlated with the real one. And if you take that correlation and square it, you get our friend r square. So then we have used models with multiple slopes at this point, but only for one predictor. Now we're talking about having predictors combined in the same model and essentially fighting it out to see which one is still standing, so to speak. There are tons and tons of research questions that are phrased this way. It's a very common thing to say, does X matter after controlling for Z? And every field has some kind of covariate that you have to control for no matter what. And so these types of models then are often estimated in a stepwise fashion. Like, let's see what happens if I put just the covariate in. Now let's add some other stuff that I care about and see if they matter after controlling for the covariate and vice versa. So you'll get a chance to practice this sort of stepwise sequencing of predictor additions in your next homework. So once we have more than one predictor in the model, the way that we interpret the slopes has to change a little bit. A slope will always be the change in y for a 1-unit change in x. That part's the same. But we have to add an additional caveat to it, that it is the change in y for a 1-unit change in x after controlling for the slopes of the other predictors. And so the terminology that I use to convey that is the term unique. This is the unique effect of x1 after controlling for x2. This is the unique effect of x2 after controlling for x1. The other part of it is that the standardized slopes that you get as effect sizes are no longer going to be equivalent to the Pearson correlation. We are going to need to get a slightly different version of an effect size that captures the unique role of each predictor in the model, and those are going to be semipartial correlations, as they are called. So a little bit of new vocabulary, a little bit of new concepts, but a lot of the same stuff that you know from before. So to illustrate the new part, I'd like you to meet the cast of This Is Us. No, for real. This is a show on NBC. It's been around for maybe 4 years now, give or take. It's a good show. And so does anyone watch the show? Who's here today? Ish? No? Okay, well, I'll give you a very brief summary. So this show follows the same family back and forth through time. And the show opened with the children of the family as grown-ups. So here's the first picture here on the left. Mandy Moore is everything. Indeed, she is. That cannot be Jack. That must remain Jess from the Gilmore Girls. See, I didn't watch Gilmore Girls. I'm like the only girl on the planet who did not watch Gilmore Girls or Dawson's Creek. They're gonna like take away my woman card from me for that. But I'm trying to make up for it now with that. I know. Thanks to the beauty of Netflix and Hulu and all these places, you can watch any show that you missed the first time around. I recently rewatched all of Ally McBeal, by the way. I watched that in college. It's still really good. And Robert Downey Jr. was everything in that show. Thank you very much. It fell apart when he left. But anywho, on to this show for today. So here's Jack, here's Kate, and here's Randall. And they were turning 37 years old, I think 36 years old when the show opened. And here are their parents, which are actually younger in real life. I believe Mandy Moore is younger than her supposed children in real life. And this is the same family then when they were like 11 or 12. So they go back and forth in time, and like you find out, initially say that Jack is dead by the time the kids are all adults, but he was still alive when they were 11, so what the hell happened? Turns out Jack got killed by a crock pot that caught fire in his house. And that was an episode that aired after the Super Bowl. So that's how big of a deal this is. Anyway, I'm using them as a story to illustrate regression. Stay with me here. So let's just say, hypothetically, we have 3, 11, 12-year-old children in the house. They're messy. Rebecca has had it. Rebecca, Mandy Moore, is everything. She always looks perfect, always sounds perfect. And she wants to make a deal to incentivize them to clean the house. So let's say the Pearson house has 10 rooms in it. There's 4 bedrooms. They each have their own 2 bathrooms, 1 living room, 1 kitchen, 1 dining area, 1 garage. So she incentivizes their cleaning by saying that for each room that each of you cleans by yourself, you get a new Nintendo game. So back when this was airing, Nintendo was everything, like the first one, with the cartridges and the gray box. That's what I'm talking about. But she also wants to make sure that it's not just an individual effort, otherwise Randall will do everything, because that's how Randall rolls. So she offers a bonus that if at least 8 of the rooms get cleaned, the family gets a new TV. That's how desperate she is to clean this house. So she decides to let them allocate their effort. She goes out shopping, or Rebecca-ing, or whatever she's doing, and then she comes back to the house and asks what happened. So let's say that this is the report that they give them. Jack claims to have cleaned the master bedroom. Kevin claims to have cleaned his bedroom. Kate and Randall each cleaned their bedrooms. Jack also tried to do the kitchen and the dining room. Kevin also claims he cleaned the living room, but Kate said she did too. And Randall, of course, does everything. So 9 out of the 10 rooms are cleaned. No one tried to do the garage, but So the family does get a TV, but then how do we deal with the overlap in terms of their individual efforts? How do we assign the Nintendo games? Well, Jack, Kevin, and Kate each cleaned one room uniquely that no one else said that they did. So in that case, we can give Jack for the master bedroom because we know that no one else touched it. It had to have been him that cleaned it. Likewise, we can give Kevin, Kate, and Randall credit for their own bedrooms, as well as Randall credit for doing the bathrooms. But for the rooms that people cleaned in common, we don't know who really did it. So it wouldn't be fair to try to guess and allocate the Nintendo games to those people. So we care about simultaneously the idea that most of the rooms in the house got clean, but that for some of the house, we're not able to allocate individual credit. Okay, with me? So what I'm talking about is this. The idea of common versus shared contributions to a prediction. So when we put multiple predictors in a model, when we have multiple people cleaning the same house, we care about the general utility of the model. On the whole, how well did the set of predictors do? What's the R-square for the model of all the family working together to clean the house? But we also care about the specific utility of each predictor. Is each predictor pulling their own weight, so to speak? Or is it redundant? I mean, could we just tell Kevin to get lost because basically the rest of the house is fine and they would have taken care of it? I don't know. So these sorts of ideas of common versus unique are often described visually with this sort of thing. I know this as a Venn diagram. It was also called a ballantine. You've probably seen these sorts of things before. Not to be confused with Valentine's Day, which was in February, according to my son. B and V are not separate letters for him yet. Also, T, F are not separate. So it's 1, 2 free, and also happy birthday, depending on the context. But anywho. So if we have Y as our outcome here, what this picture is showing is a relative carving up of Y into common versus unique elements. So in this picture, I only have 2 predictors, so 2 people cleaning the house. And the area that's labeled A is the part that X1 relates to Y and only X1. The part that is labeled B is how X2 relates to Y and only X2. And the part C is the middle part that's up for grabs, that's in common. C for common, you can think of it. It's the rooms that got cleaned, but more than one person said they did it, so we can't give them credit. And E is the part of the outcome that none of the predictors is related to. That would be like the garage that was left uncleaned in this example. So the good news is that this overlap here still contributes to the model R-square. The bad news is that none of the individual predictors is going to get credit for it. And as you might imagine, the more related your predictors are, the harder it is to try and pull apart which ones are contributing uniquely and which ones are just riding the coattails of the others. Okay, how are we doing? Good?
May I ask a question?
You may.
So I guess the way I'm kind of thinking about this is in terms of my work is like if we have a child in clinic and we're looking at their challenging behavior and say they have multiple diagnoses, say like autism, ADHD, intellectual disability, and let's say they take risperidone as well. So I'm looking at that as like, all the overlapping things that do we say E or Y was like the outcome, RP? So
Y is the outcome.
So yeah, so leading to our behavior Y, and then like from there we try and figure out what's overlapping to cause the behavior, and are they all equal? So I'm getting that right?
Yeah.
I think.
Yeah,
Okay.
I think to keep the context the same, you'd have to be talking about a sample of children that have multiple diagnoses and multiple, I think you call them comorbidities. At least that's what I'd call them in my world, but that's probably not the nicest way to put it. twice exceptional, or whatever, that all of the language, the idea that you have multiple things going on at the same time. So in order to be able to pull apart, like, is it really this characteristic or this other characteristic, you'd have to have at least some kids that only have one or the other and not both. But yeah, I think you can think of it that way. Is it the medication? Is it the diagnosis? Is it the family background? Is it, the child's whatever else? Is it whether they have a dog or a bird? So yeah, I think you can apply it to that context, because if you want to know what's really causing the behavior, to the extent that all of these factors are intertwined, it gets very challenging to isolate the effect of any one. And that's where in science, that's why we design experiments, right? Where we purposefully say, you can only have this and you can only have that. And we randomly assign people to those conditions, so there can't be any other reasons. And then we look to see, what happens or who does better or that kind of thing. In real life, you don't always have that capability. You can't randomly assign some children to an autism diagnosis and some children not, right? You can't take newborn twins and make one of them a lifetime smoker and the other one not, to see what the actual, whether smoking causes cancer is, right? We can't do those sorts of studies. But yes, thank you for the example. Fayaz, can you think of anything from your research world that would work as an example for this idea?
Can you give me a minute to think about it?
Yeah, sure. Yeah, Emmy or Jin, do you want to do that? Any examples come to mind?
Yeah, I'm thinking of similar to Alex, where we have different diagnostic groups related to reading performance was one study that I was involved in. So dyslexic versus average versus the comparison group we were looking at was cleft lip and palate. So which of those three groups related to reading ability?
And then would there be another predictor that you would expect to be related to group status?
Yeah, we had age, grade, and overall IQ also. It's comparing those as other different factors.
So to the extent that those things are intertwined to some extent, then it gets more difficult to look at what is actually driving reading challenges or reading success. So.
Yeah, so I have an example now. In my research, I'm currently trying to find out a relationship between video gaming habits and behavioral problems, right? So right now I'm looking at 4 different behavioral problems: anxiety, antisocial tendencies, depression, and the likelihood of getting into peer conflicts. And so, like, I found relationships of video gaming with all 4 of these, but these 4 actually, affect each other as well. So there, anxiety and depression go hand in hand. Depression, and both these two go hand in hand with ADHD. So it's hard to, quantify individual effects. That was one of the problems that I faced when I wanted to, form the models.
And then, of course, you have parents like me that are like, no, if my son wasn't addicted to video games, I would never have a moment's peace. So it's not the video games that are the problem. It's bad parenting. But I'm a good
No,
parent, so it's fine.
I'm
Right?
I'm looking for the opposite effect, and I found the opposite effect. Video games
Nice.
actually help. It's positive.
Woo! Parent of the year. So yes, video games as a way of reducing anxiety and depression, right? Because it's coping and it's fun, and it can be social too. So.
It is so social right now, and that's the thing. And video games these days could be so vivid. So like this morning I was looking through a game called Before I Forget, which is about like a first person. So when you think about first person shooters, you think about Call of Duty and first person, like you shoot and kill people. But this one was all about getting a first person experience of dementia. So you play as that person who goes through their different stages in life as things start to become like colorless, and you
Wow.
start forgetting things. So that was something interesting. Yeah. So games are
Wow.
good.
Yeah, that is something. That I can see that as an empathy building tool rather than just a recreational time. But yeah, so what you were talking about, by the way, if you wanted to predict anxiety, depression, and all of those things simultaneously, then you would need what's called a multivariate version of this model, where you predict them all at once. And the benefit of doing that is that you could look at how related they are. As you pointed out, these things don't occur in isolation, but you can also test whether or not video gaming is differentially predictive of anxiety versus depression. So if you put them onto the same scale, then you can actually test the difference in the slope for how video gaming predicts anxiety versus how video gaming predicts depression. Is it a stronger relationship for one versus the other? So there's a lot of things that multivariate models can buy you in terms of additional questions you can ask about these relationships. So very cool. And then there's the whole world of mediation too, which is not this class, that's the next class. So anywho, a lot of research applicability of these concepts is where we're headed here. And math. So I have all the math in the slides. I am maintaining my promise. I don't need you to memorize any of this. I want you to hang on to the big picture concepts, and I want you to learn how to make SAS and stay to do the math. So if I have a one predictor model, then the intercepts and fixed slopes are easy to find. The intercept is just a function of the difference in the means here, and the slope is a function of the correlation and the variation in each variable. For a two predictor model, it's equally easy to find, but there's a caveat here where we have to adjust for the covariance between the two predictors. So the relationship that is given by the slope is not just how related the variable is to the outcome. It's how related the variable is to the outcome uniquely after taking away any common association with the other model predictors. So you can see the term in here that shows up. The correlation between the predictors is subtracted out of the information that goes into making the slopes. So then in terms of how we quantify the unique contribution and how we would assign an effect size, we can't use Pearson correlation anymore because Pearson correlation is a bivariate indication, right? Two variables at the time. What we need is a correlation that is multivariate, that can adjust for the relationships among the other predictors and or the relationships with the outcomes. And so there's two that you will hear about, and they go by god-awful confusing names. There's partial and there's semi-partial. And semi-partial is the same thing as part. And I did not make up these names, but you will see this on your output, and so I want you to have been exposed to it. So what we're going to work with is semi-partial correlation. That is the correlation for each predictor as it relates to Y after controlling for the relationship of the predictor with the other predictors. And if we take that semi-partial correlation and square it, that tells us how much of the R square that predictor is assigned, has contributed uniquely. And so semi-partial R square is going to be our new effect size that gets spit out by the program that talks about not only a standardized way of expressing how related the predictor is, but it's standardized with respect to the R square. So if my R square is 10%, I could see that X1 got 5 of that and X2 got the other 5 or something like that. But that would only happen if there was no point of overlap. So what would probably be more likely to happen, given this picture in which these look like they're equal contributors, if I had an R square of 10%, I'd probably say that about 3% of it came from X1, 3% of it came from X2, and the other 4 is from their common that neither of them gets credit for. But the common part still shows up in the R square. So then the area A here would end up being the semi-partial correlation squared for that predictor. B would be the same thing for the other predictor. C doesn't get a name, but it does contribute to the R square. So the overall amount of variance that's accounted for is a function of each predictor's contribution as well as the joint contribution. So we're going to start seeing a term on the output, semi-partial correlation squared, which is abbreviated eta squared. So you will see that in SAS in particular. Stata is less flexible in providing these things, but I'm going to show you a workaround that I figured out for this. So semi-partial correlations are the new game in town. Partial correlations are not really things in terms of models. They exist, but they don't really answer any questions, and so I'm not going to focus on those too much. So where they come from then, semi-partial correlations are very related to standardized slopes. You can see that in each of these here, the numerator part is the same and the difference is in the denominator. So standardized slopes provide the unique covariance of each predictor with an outcome relative to its unique variance, whereas semi-partial correlations are relative to the unique standard deviation. So it's these two things are just on slightly different scales, but they're telling you the same type of information. It's a way to take the slopes that are unstandardized and put them onto a metric in which you can compare them to each other directly, regardless of the units. So these are handy dandy effect sizes that we can learn to ask for. R square then, I have a couple different formulas here that I found that describe how R square gets computed in these models. The key idea though is that it factors in the common part. So an R square can be strong even if each predictor has a weak unique contribution if the predictors themselves are very highly related. So you can't just look at the contribution of each predictor. You also are still going to be looking at the overall quality of the model as indicated by R square, and you'll have an F test that goes along with that. All right, let's see, how are we doing on time? We're still alive. So two predictor variables. Then the way that we talk about them is very similar to how we've been talking about them, just with the switch in terms of the conditionality. So in talking about, say, beta 1 in this model right here, it's the change in y for a 1 unit change in x1, holding x2 constant. So there's different ways that people talk about this. I've tried to give you all of the synonyms that I could think of. I would say that you're either taking x2 and controlling for it, holding it constant, or saying this is the unique effect. So I don't care which of these you pick. I like unique. So if I were writing something like this, I would say that each slope represents the unique effect of that variable, holding all other predictors constant. And then I would just use normal language from there. So introducing that caveat of conditionality and uniqueness first, because it applies equally across all the predictors. So each of those would have the same way. Keep in mind that you cannot directly judge the relative importance of beta 1 and beta 2 in these models unless they're on the same scale. So these are unstandardized slopes in units, and so you can have a slope that's huge because of the units and a slope that's small because of the units, and they don't have a direct correspondence to effect size. So effect sizes will be everything in these models in terms of seeing, relatively speaking, which predictors are more important. All right, standard errors then. Standard errors are the same as well, with one catch. So previously, when we had a standard error for one slope in a model, it's a function of the leftover variance in y, and it's a function of the variance in the predictor, because standard errors are scaled in the same units. But now, it's not just a function of the predictor variance, it's the unique variance in the predictor in particular. So this can cause standard errors to go a little bit haywire to the extent that there's very little unique variance in a predictor. So if you have a whole bunch of predictors in the model that overlap a lot, their standard errors are going to be higher than predictors that have less overlap. I have a slide on this coming up, but there's a term for it called either collinearity or multi-collinearity. That is not a thing anymore that you necessarily need to worry about. It used to be that, like in the 1960s, that computers would throw up when they hit predictors that are too correlated. But all of those numeric instability and computation speed issues have pretty much been solved. So that's one of the things reviewers love to harp on. Oh, multi-collinearity. Your predictors are related. Yeah, no shit, they're related. We're in the social sciences where everything is related. It's not a problem mathematically. it gets to be a problem from an interpretation standpoint. Because if you want to make a pitch that, oh, this predictor was significant and all these others weren't, and so this one's really super duper important, you have to realize that all of the other ones could have been significant in a different model that may have resulted in the same R square because they have so much overlap. So it's more of an interpretational issue. The more related your predictors are, the harder it is to say what they do uniquely. That's just the way it is. There's nothing you can do about that other than get predictors that are less related to each other. So that's one thing to watch for in models in general. It tends not to be any sort of issue in these models, but in more complex models, particularly generalized linear models, you can end up with a result where the program says, oh, everything's fine, and then you get like a standard error of 32,000. If you see something like that, it's like, nah, everything's not fine, I don't believe you. But that won't happen within general linear models. All right, so then effect sizes, there's two that I'll show you how to get. Standardized slopes is probably the more common of the two. So this is what you've already learned how to do. The beta option in state as regress or in proc rake, you can ask for standardized slopes. Standardized slopes are weirder when you get to models that have interaction terms, because there's an order of operations that matters in standardizing that can yield different effects. So we haven't talked about interaction terms in general yet, but we have seen one specific instance, which is a quadratic term. Remember quadratics? Yeah, one variable times itself, squared terms. So if I wanted to get a standardized slope for a quadratic term, if I standardize a variable and then square it, I'm going to end up with a different result than if I square my variable and then standardize it. So that kind of ambiguity makes standardized slopes less useful in more complex models where you might have these higher order terms. Semipartial R and R squared, or eta squared as it's known, is a more general way of assessing effect size, and the benefit of it is that you can also lump together slopes and get their semipartial correlation as a set, the contribution to the R square for that set. And so that will be the one new thing in terms of code that I have to show you in this unit, is how to ask for the joint contribution of new slopes in a model and to get their effect size in an eta squared metric. There's also another version of this, by the way, that's called omega squared, that W looking thing, and that is analogous to adjusted R. It corrects for lower sample sizes, so that is provided as well. All right. Yeah, that's good enough for right now. So, do I want to do this? Nah. Yeah, okay, I'll do this one little thing here. One catch on this is there are certain situations in which you should not look at a semipartial R square for one predictor, and it's in this sort of dummy coding situation, or well as the quadratic situation in which one parameter is dependent on another. So like if I have this model right here for H, I have a linear effective age as beta 1 and I have a quadratic effective age as beta 2. This linear effective age is conditional. It is specific to when the predictor is 0. So beta 1 in this instance is the slope at age 18. If you ask for an eta squared for that term, it will necessarily be different if you center age at a different point. It doesn't mean that the variable is less important. It just is conditional because of what it means in the context of this quadratic. Likewise, if I have a model like this, if I have beta 1 that distinguishes the middle group from the low group, and I have beta 2 that distinguishes the upper group from the low group, because these two slopes share a common reference group, you can't add together their semipartial eta squares. You'll actually go over what they should have. So these two slopes together create 3 possible differences. In order to get the correct eta squared for them, you have to lump the 2 slopes together. So SAS provides a way to do that very easily. Stata, you have to do a reduced model and then calculate the difference in sums of squares, but I'll show you how to do that. So that will be the one new thing that we learn, is how to get joint contributions of slopes via F, as well as their effect sizes for them. So not a lot of new stuff. Yeah. I'm just debating on how much I want to do this. I don't know that I want to do this yet. I think I'm going to stop and say, how are we doing? Feeling okay so far? Yeah. So the good news, there's really not very much new in this unit in terms of concepts. It's the idea of putting multiple predictors in the model and looking for their unique contributions, and finding one new set of code that allows you to get the contributions of multiple predictors at the same time. It is going to be a statement in SAS called contrast and a statement in Stata called test. That's the new thing. Everything else will be just a review of what you've already seen. So that means that at this point, if you wanted to, you could do the vast majority of homework 5. The new part of asking for a significance test for the change in R square from adding multiple predictors to a model. That's the new thing we haven't talked about yet. But I'm willing to save that until next week if you are. Does that seem fair? All right. Questions or comments?
I say thank you again.
Is that a question or a comment?
A comment, should I clarify?
You're welcome. There, I turned that into a question. You're welcome. No? All right. Should we call it a day then? Yeah, we're hitting that point. So, it was not garbage day, which means I say have a good weekend. Let me know if you need anything. Homework is due on Monday, and if everybody finishes it on time, we can go over it as a group if needed. So we'll see. All right. All right. Bye, everybody. Thank you. See you next time.